Good day. For those of you who don't know me, my name is Douglas Harder. In this topic, we're going to look at the heat conduction or diffusion equation. So in this topic, we're going to start with some background. We're going to review the numerical approximations we found to solutions for boundary value problems using finite difference equations. We'll then look at the physical problem and some of the properties of the heat conduction and diffusion equation. We'll examine the equation and convert it into a finite difference approximation, and we'll use that finite difference approximation to find numerical approximations of the solution. We'll consider numerical stability, look at some examples and some animations. So by the end of this laboratory, you're going to understand the heat conduction diffusion equation. You will understand how you can approximate a partial differential equation using finite difference equations, and you will be able to set up a solution to the heat conduction diffusion equation in one spatial dimension. So last week we were looking at approximations of solutions to boundary value problems. We were given an ordinary differential equation which was defined on an interval AB. We then had two boundary values, and given this we attempted to find a solution that satisfied the ODE and both boundary values. The way we did this was that we broke the interval AB into n different points. We approximated, or we said that we would approximate the solution at x sub I by some unknown value u sub I. Now this led, using the finite differential equation, to a system of n-2 equations in n-2 unknowns. We were therefore able to solve this tridiagonal system to approximate the solution at each of those interior points. Now, the heat conduction diffusion equation depends on the characteristics or properties of materials both in space and time. So therefore we have a partial differential equation where the rate of change over time is proportional to the Laplacian of the function. So in one dimension, the Laplacian simplifies to the concavity with respect to space. So the rate of change of the function over time is proportional to the concavity with respect to space. Here, kappa, strictly greater than 0, is said to be the diffusivity coefficient. So suppose, for example, as a motivating example, we have a metal bar that's already in contact with a body that's at 80 degrees Celsius. Now over time, the entire bar will therefore approach 80 degrees Celsius. Suppose at time t0, however, we place the other end of the bar in contact with a body that's at 5 degrees Celsius. Initially, you would expect it to cool down very rapidly close to the cooler body. However, over time, you would expect the cooling to move from a uniform gradient from 80 degrees linearly down to 5 degrees. This again is a characteristic of temperature. Temperature is nothing more than the vibrations of the individual atoms and molecules. Now, how are we going to describe this? Well, we're going to describe the temperature as a function both of space and time. We want to know what the temperature is here initially, and we'd also like to know how that temperature at that point changes over time. Now, other applications, and they're often going to use 2 or 3 dimensions, include the heat equation, fixed laws of diffusion, and thermal diffusivity of polymers. Here's some nice animations. On the left-hand side, we see an animation of a region that's hot in a crescent shape. However, once the temperature starts diffusing throughout the neighboring cooler area, again, the temperature in the cooler area warms up, but the temperature in the initially warm area starts to reduce. Here's a very nice example of what's actually happening. Now, if you have a box that has just a single particle in it and you remove a barrier, well, the particle will still simply continue to move. However, if you start with a region, a bounded region that has a number of atoms, and remove the barrier, then the atoms are going to start interacting. They will be pushing each other, bouncing off of each other, and pushing some of them into that other region. As you increase the number of atoms to the point, to the level of, say, Avogadro's number, you can essentially approximate all of these atoms and molecules and their interactions by continuous functions. That's essentially a summary of how we get the heat conduction diffusion equation. However, you're going to derive that much more thoroughly in your courses. Now, for those of you in computer engineering, you can even use the heat conduction diffusion equation for human vision. So diffusion is used for enhancing coherence of images, and in this case, we're working in the scale space. So last week we saw a related ordinary differential equation. However, this was simply the Laplacian in one dimension. So the Laplacian in one dimension simply says that it is an ordinary differential equation saying that the concavity is 0. Now in Lab 1 we saw that given Laplace's equation in one dimension and two boundary values, there is only one solution, and that is a straight line that connects the two boundary values. Now suppose that we have a function u that depends both on space and time, which satisfies Laplace's equation at some time. So at some time t, the concavity of the function along the entire interval is 0. What does that say about heat conduction or diffusion? Well, recall that the equation says that the rate of change over time is proportional to the concavity, but if the concavity is 0, well, there is no change in the system. So essentially we are in steady state. There is no change in our function over time. So it doesn't matter what value of t you use, they're all going to be the same. However, suppose that our function does not actually satisfy Laplace's equation. This is more interesting. And so now we know that the rate of change is proportional to the concavity. But what does that actually mean? Now recall that kappa is assumed to be greater than 0. So visually, wherever u at a point is actually concave up, as in this example, then over time the value at this point x will start moving up. Similarly, if we're at a point where the function at a particular time is concave down, then over time at that point the function will be moving down. Now of course, for any function you may have regions that have both positive and negative concavity. Wherever the function is concave up, it will move up. Wherever the function is concave down, you will see it dropping. Ultimately, the concavity, however, is going to disappear. We're going to approach a straight line, at least if the boundary coefficient or boundary values are fixed over time. So let's go back to our example. Here we see a heat conduction conduction problem. The bar is in contact with a body at 5 degrees Celsius. At time t0, we place it in contact with a body that's at 80 degrees Celsius. The bar is going to warm up, and so we have a system that at time t0, the temperature along the entire bar is 0, or 5 degrees Celsius. However, suppose we now at time t equals 0 place the left-hand side in contact with a body that is at 80 degrees Celsius. That side of the bar starts to warm up, and it warms up very quickly. And the region very close to the body that's at 80 degrees also warms up. While over here, close to the body that's still at 5, initially nothing is happening. Why? Because it's still a straight line. There's a straight line, so there isn't much concavity, so there isn't much change. However, here where you have significant concavity, you start seeing significant change. But over time, you'll notice that this essentially becomes a straight line, meaning that the concavity is approaching 0. If the concavity is approaching 0, that means the rate of change of the system is also approaching 0. It's approaching the steady state. So as the concavity becomes smaller, the rate of change also decreases. Here's a different example. Suppose we start with a bar that's at 100 degrees Celsius. We place that bar between two bodies, one at 80, one at 5 degrees Celsius. What do we expect to happen? Well, again, both ends will drop, and over time, we expect the bar to approach the solution to Laplace's equation. It will be linearly decreasing from 80 degrees down to 60, down to 5. So ultimately, there will be no difference. It's going to approach the solution. So here we have the temperature initially at 100 degrees. uniformly across the entire bar. So as we let the system progress, initially you get change at both ends. However, ultimately you're going to get concavity along the entire bar, and you get a very rapid change. As the concavity disappears, the rate of change decreases as well. Ultimately, the concavity is going to disappear, at least if the boundary conditions remain constant. Now, you're going to look at some cases where we actually change the boundary conditions over time. However, at least if we're leaving the boundary conditions constant, it approaches a straight line. But this is only going to be true in one spatial dimension. In higher spatial dimensions, instead, again, assuming constant boundary conditions, it's going to approach a solution to Laplace's equation. However, that may not actually be a smooth or a flat surface. But we're going to see that in future labs. Now, for any such problem, what do we have to know? Well, we have to know what the initial state is along the entire bar. If I tell you that I know that the initial temperature of the bar along here is 5 degrees, but I have no information about what the temperature of the bar is over here, how can I approximate how the temperature progresses over time? I must know the entire temperature of the bar at our initial time t0. So essentially we must have some function that defines our function at time t0. Also, we would like to approximate the solution up until some final time t sub final. We could go to infinity analytically, but numerically we have to stop at some point t sub final. Now, also to do this, we need two boundary values. We have to know what the temperature is on either side for all time. For example, if I tell you that we start with a bar that's at 0 degrees, we place one side in contact with a body that's at 100 degrees Celsius, but we have no information about what the temperature on the other side is, the behavior is going to be very different depending on what that temperature is. So you must have both boundary values. You must know what the temperature is here and the temperature at the other end. So we will need a function that gives us the value at the left-hand endpoint, and this function is a function of time, and we must also know what the state of the function is at the right-hand endpoint as well for all values of time. So both of these must be known from t0 until t final. Now, as with boundary value problems, we're going to do the same thing. We're going to take our spatial dimension and we're going to divide the interval AB up into n sub x equally spaced points, and the width of each interval will be said to be h. Similarly, we will divide time into discrete steps, just like we did with our initial value problems. We divide the interval t0 to t final into n sub t points, and each interval, or the distance between each point, for now will be a constant or a fixed value, delta t. So this is going to give us an n sub x by n sub t grid of points. So we will approximate the region that we'd like to solve over by a bunch of points. So these points here represent our initial state, and we will then try to approximate the state as time progresses up until our final time. How will we approximate this? Well, we will approximate the value at some point xi tk by some unknown value u sub I k. Now, how are we going to approximate these partial derivatives, and what are the required conditions? Well, first of all, recall that our approximations of the derivative came from the last class. So we could approximate a derivative using the centered divided difference formula both for the first and second derivatives. However, in this case, we're dealing with partial derivatives. But remember that the definitions of partial derivatives are very similar. They're both limits, but you only vary the variable that you're differentiating with respect to. So in this case, we're differentiating with respect to space. We only vary the first variable. Differentiating with respect to time, we vary the second variable. Now for clarity, in all of these labs, we will always use h for a small step in space, whereas delta t will be a step in time. Now, it's rather obvious that we can do approximately the same thing we did with derivatives. We just chose a finite value of h or a finite value of delta t, depending on whether or not you want to use a forward or center divided difference formula. Now, recall, however, that we're going to be approximating the solution on a grid. So our approximation at a point u sub an approximation at x sub I t sub k is approximated by some unknown value u sub I k. Now, xi and tk are already defined. But if we substitute x sub I and t sub k into our formula for the derivative, we get x sub I plus h minus u at x sub I, both at t sub k. Now recall that x sub I plus or minus h is just x sub I plus or minus 1, and the same for t sub k. So we can replace this first term with x sub I plus 1. And we are approximating u by some at x sub I plus 1 t sub k by the unknown variable u sub I plus 1 k. So there we have our approximation in terms of the points on our grid. So we can substitute these into our formulas, and now we can approximate both partial derivatives on this grid. Similarly, we can approximate the second partial derivatives. Now, one problem. We could use the center divided difference formula, but we're only given the initial state at some time t naught. And thus we can't really use 3 different unknowns in time. We can only look forward. So we're going to use just the forward divided difference formula, at least initially. So we're going to approximate the rate of change over time by this formula. Let's substitute that into our heat conduction diffusion equation, and we do so to get this. And solving for the state in the future, we get that the state in the future is equal to the state at u sub ik plus delta t times kappa times the concavity. Now this should look actually quite familiar. In fact, recall Euler's method. Euler's method says that if we have a ordinary differential equation with some initial condition, we can approximate a solution to that system by just setting the next value is the previous value plus delta t times the slope. And that is the slope at t sub k, y sub k. Now, the next step is to approximate the concavity. Well, let's just substitute the same formula. We're going to use the finite second order centered divided difference formula to approximate the derivative. Substituting that in gives us this equation. Let's collect kappa, delta t, and h. And so we get that our approximation at the next point in time is our approximation at the point in time k plus this coefficient with this difference of values at time t sub k. Now, one interesting question is what happens if that ratio is too large? So if h is small, h squared is much smaller, and that ratio could potentially become very large. That's an issue we're going to look at later on in this lab. However, we now have our finite difference equation for approximating the heat conduction and diffusion equation. Now, graphically, you notice that u sub I k plus 1 depends on a linear combination of 3 values at the previous state in time. So at time tk plus 1, the value here depends only on these 3 values at time t sub k. Well, this is actually useful because we actually know what the initial state is along the entire interval, and therefore we can always start stepping forward. Now, for first order ODE, we always require a single initial condition. However, for a second order ODE, we have a choice. We can either have two initial conditions, so the initial value and the initial slope, or, and again, this is usually what happens when we deal with time, or we can have a boundary condition. So if we're dealing with space, very often we will have an interval and we will have boundary values on that edge. Now, for the heat conduction diffusion equation, we have a single partial derivative with respect to time and a second order partial derivative with respect to space. Therefore, for each coordinate in space, we will require one initial condition. What's the initial state at this point in the bar? But for each time coordinate, we will require both boundary conditions. Now, in this case, we will require an initial value for each space coordinate. We are in one dimension, and so essentially we will need to know what the entire state is at the initial of the bar at time t naught. Now, if we were monitoring the diffusion of a gas, then we would also instead have to know what the concentration of the gas is at some initial point. Now, up until now I've been discussing bars. Is the heat conduction diffusion restricted to one dimension, only applicable to bars or thin tubes? Well, not really. Most systems have symmetry that allows us to simplify the model of the system. So for example, you might have a thin insulator between two materials that have significantly different temperature. Alternatively, you may have two different concentrations across a semi-permeable barrier or a membrane, and you're determining what the diffusion is across that barrier. So the fact that we're doing this in one dimension may actually not be that simplified. It actually does have applications. Okay, going back to our boundary value problem, we divide the interval up into n sub x points, and our first point is A, our second point is B. Now, at each of those points, we need to determine what the initial state is. So we're going to have to pass in a function u sub init. U sub init is a function of x, or space, and it's going to map the interval onto some value r, or each point of the interval onto some value r, the initial state. Now, as with Euler's method and other initial value problem solvers, we will also divide the time space into intervals. And so at time t2, the next point, we will approximate the solution using our information at time t1. But we will require the two boundary values. So we need to know what this value is and what that value is. Similarly, at time t3, we will need to know those two values, and so on and so forth. So we will need to know all of these as initial values, and we will need to know all of these values as boundary values. So we require functions, a sub boundary of t, b sub boundary of t, which we can give at these times, and it will return the boundary values. Now that we have our initial conditions defined, our boundary conditions defined, essentially what we will do is we will always step forward. We will take our initial state using the heat conduction diffusion equation. We will approximate the solution at each of the interior points at time t2. Then, having found all of those, we will approximate the solution at each of the interior n sub x minus 2 points at time t3, and then t4, and then t5. This sounds a lot like a for loop. Hopefully that makes sense. So that will give us approximations along the entire time period. Now, this really suggests that we will be using a matrix. Given the heat conduction diffusion equation here, we will approximate the solution on this space interval, on this time interval, by creating a grid of n sub x by n sub t points, defining a matrix U. U sub ik is going to approximate the solution at u sub x sub I, t sub k. X sub I is given by that formula, t sub k is given by that formula, and h delta t can be calculated. Now, as with the previous labs, you are going to have to validate your arguments that are passed in and the types. Now, recall, however, that we already asked, what happens if that coefficient is too large? Let's say h is very small. Well, in that case, if that coefficient is large, if there's any sort of error in our approximation, a large coefficient there is going to magnify the error. So before we do anything, we actually have to check that error. Now, without going into too much detail, let's take a look at this total sum. If we're going to sum up the values at the next state in time, k plus 1, well, that's just the sum of the previous values plus the ratio times our divided difference for the second derivative. If we expand this out, this simply becomes the same previous sum, the sum at the previous time, plus a ratio times the slopes at either end. Now, with a little bit more work, you can see that if you have too much of an error here or here, these might not cancel out, and this might actually be a factor that contributes to the total value over time. Now, the approximation of these two slopes here, as you see, has an order h error, and I'm not going to prove it. However, I'm going to just simply state that to deal with this, we have to ensure that this ratio kappa delta t over h squared must be less than 0.5. What that will do is that will essentially create a contraction mapping here and will ensure that any error that is introduced does not actually continuously contribute to the problem. We're going to see what happens if we don't satisfy that. So in writing your function, the first thing you're going to do is you're going to have to make sure that kappa delta t over h squared is less than 0.5. And if that's not true, you're going to have to send an error message. So you might say, hey, your ratio is something that's greater than or equal to 0.5. Now, being a good user, you should actually tell the user, hey, how about considering a different value of n sub t? The question is, what value of n sub t should you use? And more importantly, how do you display that to the user? Well, first of all, we have to figure out what value we want to use. Well, what can we change? We can probably change the step in time. That's probably the easiest thing to do. So let's change the step in time and suggest to the user some number, how many points in time should we use for a given n sub x? Well, essentially we want to, this is kappa, this is our value delta t. We want to make sure that given the h that the user has already given us, we want to find an n sub t star which is large enough to make this ratio less than 0.5. Well, basically you can just solve that for n sub t star. It's not going to give you an integer, it's going to probably give you some double precision floating point approximation, and so you should take the next largest integer. For example, you should review the floor and ceiling functions. The next step in finding your approximation, you're going to have to define a column vector of x values and a row vector of t values. You'll recall with your initial value problem solver from your last term, we did return the t values as well as the approximations to the solution. Well, same thing here. We're going to return a vector of n sub x, x values going from a to b. We're going to return a vector of n sub t, t values going from t naught to t final. Both of these can be constructed, of course, using linspace, and they're both going to be returned to the user. Next, we're going to carry on by constructing a matrix of size n sub x by n sub t, and the zeros command is as good as any. Now we have to assign the initial values in the first column of our matrix. Well, that's not that hard. We know what our x values are. We found that with linspace, and we can now pass that vector of x values to our u sub init function. And we have to find the boundary values, and we can pass our vector of t values to our boundary value function that will be passed in. That gives us our boundaries, both in space and time. Now we have to calculate how the system will progress. We have to calculate those interior values. Well, this is where you're simply going to use your formula. So, given any 3 points here, you can calculate an approximation of the solution at that point. In fact, you can do so at all of these interior points by using all possible triplets at time t1. So, we can calculate approximations for u sub 2,2 all the way up to u sub 8,2 at all of the interior points. Having calculated all those, we can now approximate at t sub 3. And we can just keep on doing this up until we get to our final time. So the signature of your function, we're going to return a vector of x values, a vector of t values, and a matrix of approximations of the function u. We're going to pass in kappa, the x range, a to b, as a pair of vectors, n sub x, our t range, t naught to t final, n sub t, a function handle, and boundaries. So, kappa is the diffusivity constant coefficient, u sub range is the interval ab, n sub x is the number of intervals that we're going to divide the number of points we'll divide the interval into, t sub range is t sub naught to t final, nt will be the number of points that we divide the interval into, and u sub init is a function handle giving our initial state. U sub boundary, rather than passing a and b, u sub boundary is simply going to be a function that maps our time interval onto pairs of real numbers. The first one will be our a boundary, the second one will be our b boundary. Now, some things that you're going to need. Well, MATLAB has some very nice things to assign to entries in a matrix. For example, this first column has 4 entries. If I now say assign everything in the first column these 4 values, well, I will just reset these 4 values to 0. Similarly, I can say everything in the first row from the second to the last entry should be assigned 42. Well, there's 4 values here, there are 4 42s there, so they would all be assigned. Similarly, I can say everything in the third column, from the second to the second last entry, and there's 2 values, should be assigned this column vector of 2 values. After executing these 3, we get the values as expected, changed in the matrix. MATLAB also gives you a little bit more power when you're trying to assign submatrices. Here I'm saying I want to change everything in the first and third rows from the second to the last entry. So basically everything in the first row from the second to the last entry should be these 4 42s. Everything in the third row should be 91. And that would assign those 4 values as well as those 4 values. Another thing is throwing error messages. Now, up until now, you've just thrown a fixed error message. However, MATLAB allows you to include some information in that string that you're passing. And those of you using C or that have written C before with printf or sprintf, it's essentially the same. What you do is you have placeholders inside your string. These placeholders are prefixed by a %, and %f says you want to replace that with a floating point number. %d says you want to replace it with an integer, or an integer value. Now, how does it know what to replace the first %f with, and the first %d, and then the next %f, and the next %d? Well, it's just subsequent arguments passed after the string. So a would be replaced with, %f would be replaced with the first one, d with the next one, %f with the next one, and %d with this final one here. The output now will be, for example, if I pass it 3 and 5, first we have it replaced with a floating point 3, an integer 3, floating point pi, and a rounded version of pi. Now, you can modify this. You can actually do your calculations in there. You can just replace them. It's always %d is the first one, first argument, or the next argument, the next argument, and so on and so forth. So in this example, if you try passing it 3, 5, it's simply going to give you an error message. The ratio of 3 and 5 is this ratio a divided by b. If you need more help, just ask for help sprintf. Another very useful command is the diff command, and you should be using it. So for example, here I have a vector of some random values I typed in, and if you now call diff on it, it will calculate 3 minus 1, or 2, 6 minus 3, 3, 7 minus 6, 1, 5 minus 7, which is -2, and so on and so forth. This is essentially the same as taking all the values from the second to the second last and subtracting from it the first to the second last entries. But again, this is faster and internal. If I pass diff a second argument that says 2, it's actually going to be using the formula for the second derivative. In this case, I'm going to take this value minus twice that plus that, which is 1. 3 minus twice 6 plus 7 is -2. 6 minus twice 7, or 14, plus 5 is -3. 7 minus 10 plus 4 is 1, and so on and so forth. That's the formula that you're using over and over again. You're just multiplying it by some coefficient kappa delta t over h squared. And again, you can calculate this the long way, but diff makes it a lot easier. Now, why would you want to use diff instead of a for loop when you're writing your function? Well, you could just have 2 nested for loops, or you could have just a single for loop where you use a diff function, where the diff function does most of the work to calculate the kth column, where k goes from 2 to n sub t. In MATLAB, the reason we want to use the second format is because most commands are compiled C code, whereas any explicit for loop or while loop is going to be interpreted. For example, here is my implementation of matrix-matrix multiplication. It's about as good as you can get, checks all the error conditions, creates an output matrix, and assigns those entries. Now, let's try this out. Here are 2 matrices, M and N. They're both reasonably large, on the order of 1,000 by 1,000. If I type in tick, m times n, and talk then displays the time difference since tick was entered. So it tells you how long did it take to calculate m times n. Well, in this case, it took about 0.2 seconds. Well, how about my matrix multiplication function? 36 seconds. That's a factor of 180. Now, what's a few orders of magnitude between you and your employer? Your job? Okay. Another thing. Suppose we want to implement a function that stays on only for, say, 1 period. So this looks like a negative cosine function, but it's restricted to the interval pi over 2 to 5 pi over 2. Well, in this case, you'll recall from last term, we could actually define the function as follows. We could take the function negative cosine, and we could element-wise multiply it by this expression here. So checking that x is greater than 5 and x is less than 2.5 times pi. Now, if we actually plot this, you'll notice that if we give it 101 points, all of these points is 0, but on that interval, we get the value of negative cos of x. To understand how this works, consider a fewer number of points, 11 points from 0 to 10. If I take each of these points and ask, is it greater than or equal to 5, 0.5 times pi, well, I only get a 1 for those values of 2 up to 10. If I calculate all those points that are less than or equal to 2.5 times pi, I only get 1s for the first 7 values. If I now do an element-wise, bit-wise AND, or element-wise AND, well, now I only get these values that are both greater than 0.5 pi and less than 2.5 pi. All right, another useful MATLAB feature that you may want to use or will have to use is functions and anonymous functions, or anonymous functions. You could define the function u sub init, u sub a to a init as follows by using file new function. You could save it as the function by the file name u2a sub init, and then you can call it in MATLAB on any vector values under the assumption you used a vector valued function or element-wise evaluation within your function u2a init. And again, is at of u2a init a function handle? Yes. Alternatively, you can use the anonymous function format. Works the same way. You can call it on it. However, now the variable itself that has been assigned to is the function handle. So here's our first example. We have a state, an initial state of 0.9. We have one boundary value that's at 1.7, another boundary value that's at 4.1. We will break the interval 0 to 1 into 6 points. We'll break the interval in time from t naught equals 1 to t final equals 3 into 12 points. Kappa is going to be 0.1. Mesh, this will be your output. If you call mesh on this, you will get this graph. Notice that the temperature is initially approaching the steady state solution, and over time it's getting very close to a straight line. The size of x1 is of course a 6 by 1 column vector. T sub 1 is a 12-dimensional row vector, and U1 is a matrix, a 6 by 12 matrix. In this case, the boundary conditions are constant. So this boundary condition just returns 0.19 for everything. Or no, sorry, the initial state, the initial condition is 0.9 for all values. And in this case, the boundary values, the first row is all 0.7s, the second row is all 4.1. So just to demonstrate, your u2a init should take all of your x values from 0 to 1 with 6 of them and return that vector. Your t that is returned is going to be linspace from 0 to 3 with 12 points, or n sub t points, and we can evaluate this from the second to the last entry at our boundary values, and we will get pairs of boundary values, one at A, one at B. Now, we have a very large h and a very large delta t, so notice what happens. There's still some weird fluctuations. So it's warming up quickly, then it's warming up slower, then it's warming up slightly quicker again, and then it's warming up at a ever gradually slower rate. That's because we have a very coarse approximation, but at least that ratio is still less than 0.5. If, however, we increase the number of points, say to 104,000 points, again, this ratio with these two sets of points is still less than 0.5. Notice that we have a much smoother transition as we would expect in nature. However, suppose that we reduce this n sub t to 3,916. So now we're using fewer t values, but now this ratio is greater than 0.5. If that ratio is greater than 0.5, notice what it's suggesting. it's suggesting that there's a bulge in the middle. So our approximation doesn't make sense anymore. In fact, if you go down to 3,900 as n sub t, this ratio is only a little bit larger than 0.5, but this is saying that the temperature in the middle of the bar should now be at 2 times 10 to the 14 degrees, which is, well, unless you believe in cold fusion, absurd. Now, these images show us how U changes in both space and time, but how are we going to just visualize the temperature as time changes? Well, that suggests we should use an animation. So if you look in your laboratory directory, you're going to find a source directory that has 4 functions: animate.m, frames to gif.m, and 2 helper functions, isosurf and RGB to GIF 8-bit. Now we can call our function with some values. In this case, n sub x is 20, n sub t is 150. But now I'm just going to pass the returned matrix to the animate function. The animate function will create a number of frames, and then I can convert those frames into a GIF. Now, even in MATLAB, it will display, the animate function will actually display the animation, but you can also save it to a GIF file. And so in this case, this is the returned matrix U when displayed using the mesh command. However, once you pass the matrix U3 through animate and then save it to the file u3.gifs, we notice that we can now see how the temperature changes over time along the entire interval. So, in summary, we've looked at the heat-conduction diffusion equation, we've considered the physical problem, considered the effects in one dimension. So what's actually happening with the heat-conduction diffusion equation in one dimension? Wherever it's concave up, the rate of change of the function will be positive. Where the function is concave down, the rate of change over time of the function will also be down. We found a finite difference equation that approximates our PDE. However, we also saw that kappa delta t over h squared must also be less than 0.5. We looked at some examples, looked at supporting MATLAB commands, and ultimately we looked at some animations of our results. So, good luck with Lab 2. I hope you have a good day. Cheers.